So let's understand the velocity boundary layer. So as we said, we have fluid that flows over a solid surface, resulting in the fluid velocity being 0 at the wall due to the no slip condition. Now you have fluid molecules that are adjacent to the surface of the wall. They're going to start losing momentum because they interact with the surface and they interact with the molecules that have low velocity. And so this results in molecules exchanging momentum with each other and causing the influence of the wall essentially to extend deeper into the fluid in the y direction. And because you have such a velocity gradient, because as soon as you have fluid traveling over a solid surface and you develop that no slip condition, so you have a 0 velocity at the surface, you immediately start developing a velocity gradient. And the velocity gradient that you develop starts producing shear stress, whose magnitude is proportional to the fluid's viscosity. Now, this equation shows you how you can quantify the shear stress, and it essentially tells you that shear stress is equal to the viscosity multiplied by the gradient of the velocity evaluated at the surface, essentially. Hello everyone, I'm Amr, a chemical engineer, been working in the engineering consulting industry for about 8 years now. My goal is to bridge the gap between academia and industry, between theory and practice, and give you the tools you need to succeed as an engineer. So if you want to succeed as an engineer, check me out. So this shear stress appears as a force that the fluid exerts on the surface. Also within the fluid, the shear stress is irreversibly converted into internal energy. So for example, when you size a pump, what a pump does is it increases the fluid's mechanical energy. And some of that viscous shear converts part of that mechanical energy into internal energy that the fluid absorbs as heat. Also, I just want you to note, because now we've sidetracked a little bit, but I want you to note that the shear stress exists only because of the velocity gradient. And so for instance, when you have a pump that you have sized, what the pump does is that it allows you to maintain that velocity gradient, and that velocity gradient then produces that shear stress that converts some of that mechanical energy into internal energy that is absorbed by the fluid. Also, I want you to note that with the case of this flat plate, the velocity gradient decreases and weakens with distance from the wall. So the more you travel in the x direction, the more that this velocity gradient will start going down. And so maybe one thing you start realizing right away is that this shear stress changes as you travel along this plate. And so the more appropriate term to use is local shear stress. And we're going to see what we can do, which is we probably need to integrate over the whole plate to be able to find the cumulative impact of the shear stress. And all of this conversation we're going to have later on. But I just want to make you aware that the shear stress over here is not a constant value. It changes as you travel along the surface. At some distance delta from the wall in the y direction, the viscous effects start becoming negligible and the fluid velocity approaches its free stream value. Well, that's understandable because the wall's influence weakens the more you travel in the y direction. That's essentially what it's saying. And that distance is actually important because that distance is what defines the velocity boundary layer. And as you can see here from this picture, the velocity boundary layer at the very beginning starts very small, but then for a flat plate, it keeps on increasing the more you travel, the more the fluid travels over the flat plate. And in practice, the boundary layer thickness is commonly defined as the location where the stream velocity is at 99% of its bulk velocity or free stream velocity. And here, this graph, I was trying to make a point, the velocity gradient weakening further across the surface of the plate. So over here, you see that you have a laminar region, you have a transitional region, and you have a turbulent region. Let's not confuse ourselves with all of these regions right now. Let's just look at one region, and I'm going to talk about the different regions and why is it important to be aware of them. But let's just now stick to the laminar region for now. And let's look at two arbitrary points. Let's say I select this point, x1, and let's say I select this point, x2. And all you need to know right now is that x1 is closer to the edge of the flat plate and x2 is farther away. And they're both in the same laminar region, let's say. What you'll find is, you'll find that the velocity gradient at the surface of the flat plate at x1, which is closer to the leading edge, you'll find that a lot higher than the velocity gradient at x2. Now, there's many perspectives for you to look at this with, but I'll give you my explanation because it helps me visualize it. So if you look at the point x1, you have the boundary layer thickness that is developing has a very short distance. And that means that at the surface where the velocity is 0 because of the no slip condition, and at the edge of the boundary layer thickness where you have the free stream velocity being at the maximum velocity, you have such a short distance through which the velocity change needs to occur, as opposed to x2, where you have a larger distance through which that velocity change occurs. And if we look here at these graphs, so the first boundary layer thickness at the point x1, you could see it's a lot smaller, and so the velocity change from 0 to the maximum needs to occur in that small distance, and therefore it only makes sense because of that you'll also have a velocity gradient at the wall where y equals 0 being a lot higher than at point x2. If you look at the slopes, well, you actually want to look at the inverse of these slopes, because on the y-axis I have the vertical distance and on the x-axis I have the velocity. But when we're looking at the shear stress equation, we are actually wanting to see the change in velocity over the change in the distance. So you're looking at the inverse of these slopes. And essentially what you can see is that the slope at x1 will be a lot more steeper than the slope at position x2. And that was the point of this visualization. Also, as a side note, this is not a fluid mechanics class and this is not a pump sizing course, but just as a side note, the friction losses that we used to figure out the major or minor losses in pipes, they essentially represent the mechanical energy dissipated within the fluid due to the viscous shear stresses generated because of the velocity gradients. That is essentially what you do when you size pumps, but a lot of people can size pumps and you don't necessarily need to know things on this level of detail. Like, for instance, a lot of people can size heat exchangers without necessarily understanding boundary layer theories, but it's good to put the pieces of the puzzle together when you have the chance. Okay, so now you might wonder why the velocity boundary layer and these different flow regimes like the laminar, transition, and turbulent matter for thermal transport. Why are we talking about this? Well, heat and momentum are transported actually by the same physical mechanisms. So in laminar flow, the transport method is due to molecular diffusion. And in turbulent flow, you have turbulent eddies. And so depending on what the flow regime is, it directly impacts the heat transfer behavior. And I want you to be aware of that, because when we start looking at the boundary layers for thermal transport, and when we start looking at the heat transfer convection coefficients for different geometries, you might see different correlations for laminar flow than for turbulent flow. For example, in laminar region, heat transfer is primarily limited by molecular diffusion. However, in turbulent region, heat transfer is significantly enhanced because of this turbulent mixing. So let's start to understand these regions more right now and then go into the thermal boundary layer.